Good afternoon. My name is Benáçek, and well, first of all, thank you for this opportunity to present my presentation at this workshop. And basically, my presentation is about calculating of kind of radio emission using this linear acceleration emission model from bunches that are created in polar cap regions. And it turned out that like my 2 or 3 slides were basically recapitulated in the previous talk. So we assume that the radio emission comes from the polar cap regions, and there were in the past, let's say 50 years, proposed like many radio emission theories that try to explain how the pulsars may radiate. And usually this like current Croce emission assumed like in most of the studies. However, we decided to use a slightly different approach to see whether there might be a competitive theory that may explain the high observed brightness temperatures or the coherency of the waves, the polarization properties, and so on. So we assume that in the polar cap region the spark event occurs, and I will not repeat what it is. But basically, we assume that we have a gap region in which the electric or paraelectric field is very high. So eventually, the spark event occurs, and a bunch of electrons and positrons is created. And because this bunch has quite high relativistic factors, in this case along the magnetic field line, assuming that this is like one-dimensional model, the plasma outflows from this region, and the sparking event may occur after some time. Usually it is assumed like 500 nanoseconds or a few microseconds or something like that. So this repeats very fast in time along, let's say, each open magnetic field line. And eventually what we obtain is a train of bunches that evolve, move quite fast along the magnetic field line, and they may somehow interact and produce the radio emission. So it was shown also by these simulations in 2D that when the cap region was located somewhere on the left, so this region on the left, so eventually the plasma bunches or clouds of particles outflowed from this region. However, what was not sure how these bunches evolve on much longer time scales, whether they may interact, how it was proposed in the 1980s, and what are the exact radio emission properties of their electromagnetic waves, because we don't need only, or we cannot just have a look on the electric and magnetic field components, but eventually these electromagnetic waves interact with plasma, and the plasma can also absorb these waves. So it is a question whether these electromagnetic waves can escape, for example, the region, or whether the waves have such properties that they can eventually escape from the region. So these are our two questions. So first I will present briefly the bunch evolution properties. So there are like two options how the bunches may evolve in time. So first option is here on the left. When the spark event like occurs somewhere here, but the gamma photons that eventually produce the electron-positron pair, or the bunch is created somewhere outside of the strong electric field, then the electrons and positrons have very similar velocity distribution functions, and eventually when we have this like density profile of the bunch, the electrons and positrons can expand to the left and to the right quite symmetrically, and the bunches may expand, and eventually they overlap in fairly ways, as I will show you on the next slide. However, when the electron-positron pairs are created in strong electric fields, there is a difference in their velocity, and what happens is that the electrons mostly expand on one direction, while the positrons on the other direction, and some kind of effect which is known as ambipolar diffusion occurs on the edges of the bunch, and very strong longitudinal electric fields are created. And this electric field, the particles can oscillate with some oscillation frequency, and therefore emit the electromagnetic radio waves. So this is wrong version of my presentation.
Just one.
There was only one.
Yes.
So there is no other either.
You can open PDF. If
We can try whether it helps.
let's try.
Andrei, you have the PDF? Sorry, the
Yeah,
USB
yeah.
drive?
No, I saved it here.
Yeah, next. No.
No?
No. Okay, so now 2 slides are missing. But anyway, so the conclusion of this slide is that there are 2 options how the bunches may evolve. First option is that they overlap in phase space. They form relativistic streaming instability, and in this relativistic streaming instability, kind of charges, solitons, are formed, and these solitons may radiate, for example, as they move along curved magnetic field lines due to coherent curvature radiation. On the other hand, we have like this option number 2, when the bunches they don't like expand, they some kind of interaction occurs, and now next slide doesn't work.
No, it's work. Okay.
Sorry. So this electrostatic waves evolves on the edges of the bunches. The bunches are constrained from the expansion, and they may radiate somehow differently. So we wanted to analyze how they may radiate, and therefore, because these particles here oscillate along the magnetic field line, we choose this linear acceleration emission, basically meaning emission by particles that are linearly accelerated or linearly oscillating along the magnetic field lines. So I here propose like short comparison what this linear acceleration emission means. So with comparison with synchrotron emission, when we have like gyrating charged particle which emits like perpendicular direction or mostly perpendicular direction to the magnetic field line, and yeah, this is also broken. Yeah, you know the emission angle for the relativistic particle, and total emission, detected emission of the particle is proportional to gamma square. In the linear acceleration emission, particle oscillates along the magnetic field line. The emission profile in the reference frame of the oscillating particle is perpendicular in the perpendicular direction. However, these bunches move very fast with relativistic velocities along the open magnetic field lines. So the emission is like beamed into some kind of cone, and the properties are quite similar in this case. So the standard approach how to calculate the emission of some accelerated particle in plasma is using like this equation when we have direction n, or the emission of the radio emission in the direction n. Beta is velocity of the particle, and beta dot is acceleration of the particle. However, this approach means that when we have like particle initial simulation, when we track individual particles, we have like billions of particles which needs to be tracked for tens of thousands or hundreds of thousands times that, which is like basically undoable on kind of supercomputers. So we choose slightly different approach, and we use electric currents. So the particles were directly in the simulation aggregated to electric currents, and from the electric currents we calculated fast Fourier transformation and used like this equation, which is more or less they are convertible from one to other. However, these electric currents are represented in the simulation in a grid cells. So we have like just let's say 100,000 grid cells estimated for 100,000 time steps, which is significantly less computational power, which allowed us to calculate or use and utilize all the particles or information obtained from oscillation of all particles in the simulation. So and now there are some, yeah, this is just our representation. So we assume some kind of emission region, which is in our case like in a one-dimensional approach, and we have like plasma particles that oscillate, and eventually they produce the electric currents in the plasma frame, which is basically our simulation particle initial simulation reference frame. And when we calculate the radio emission in the like simulation plasma frame, we beam like relativistically it to the Pulsar frame, and we obtain some kind of properties of one interacting bunch that can be like produced in the polar cap region. And now the results. So we compare the two cases. One case with overlapping bunches in time, and so the second case bunches that are constrained from the expansion when they are created in electric fields. And I compare plasma frame with Pulsar frame. So the overlapping bunches or the relativistic streaming instability have radio emission quite like narrow band in frequency. Here is frequency, here is angle. However, after beaming into the Pulsar frame, it still is quite narrow band emission, which is up in angles, let's say, smaller than one degree. That is for our parameters. However, in bunches constrained from emission, the emission in the Pulsar frame, in the plasma frame, and also in the Pulsar frame is quite broadband and also quite intensive. And it's not seen. So we compare here, like the emission on the left is like on one pair of these bunches is 10 to the power of 8 watts. However, these bunches contain from expansion, the total power of the emission or the radio emission is 10 to 16 watt. And you can compare it with typical Pulsar radio emission, which is in the range 10 to 18 up to 10 to 22 watt. So basically we need from hundreds of such simultaneously produced and interacting plasma bunches if this like model on the right is correct, while the model on the left is probably not able to explain those relativistic streaming instability is not powerful enough to explain the radio emission, because we would need like millions or even more of such bunches simultaneously producing radio emission. So therefore, in the next slide, I'll focus on these bunches constrained from emission. So we first calculated radio spectrum, and we obtained this breadth curve, which we fitted to this standard equation that is used for pulsars. And even one interacting bunch can have very similar spectrum to those spectra obtained from observations. And also, I calculated that when as the pulsar rotates, we observe like changing intensity in time, and you can see that we have like microsecond oscillations of the intensity as the emitted waves mutually interact in various angles. And also there are two beams produced because we have like symmetric emission according to the angle to the magnetic local magnetic field line. And the intensity is relatively small. However, calculated this is emission only by one bunch, so it can be relatively easily scaled up to the observed axis by pulsars. Okay, so the exact radio coherent emission process on a kinetic microscale is still under debate. And in this study, we studied the linear acceleration emission, how the bunches that evolve in the pulsar polar cap regions may radiate.
Yeah, the problem with your model is just you assume that there are bunches, and those bunches are moving along magnetic lines, and then you calculate what they're doing. From our simulations, just they are not talking about like my simulations, they are simulations done by Sasha Filipov, there are a bunch of other people, such as Belgorodov's group. We have never seen anything which even closely resembles those bunches. So just if you want to see how the plasma density distribution looks like, just look at my paper, Timokin and Aras. You will see that there is nothing which should really facilitate bunch production. So that is the main problem. So it's all these bunch related problems. So just if you start, let's say, from the from ab initio, so just you are not going to get anything which will produce you bunches, and then by extension, all the physics. Just look at those papers. Just
well, I looked, and for example, this bunch produced by simulation by Filipov, so you don't think that it is like real.
This is a very toy model. So just you should really just think about the plasma multiplicity. This is allowed is around 3 or 4. So it's nothing like, so just what happens in the real pulsars. Just look at my paper where I have real multiplicities. Up to 10 to the 3, 10 to the 2, so just like to get a feeling what plasma density distribution does. This is artificially constructed toy model to demonstrate one effect. So just we got rid of anything which could like unnecessarily complicate it. So you should not take this literally except the wave emission, because it is designed to demonstrate that the wave is really generated. Everything else is strict away.
Yeah, thank you for your comment. I think we may discuss
Yeah,
after.
sure.